Hello, and thanks for using TickBoom. In this video, I'm working through the third of a series of 6 questions that are investigating how we can calculate volume using calculus. If you haven't already, I'd recommend taking a look at the first 2 questions that I've worked through, as they provide some good background to what these questions are all about. Question 3 says, a torus is a donut shape, as shown below. It can be created by rotating a circle about an axis. Find the volume of the torus formed when the circle x minus e squared plus y squared equals d squared, where d is less than e, is rotated about the y-axis. So here I think using the technique of cylindrical shells is probably going to be the way to go. So let's do it. So I'll just note the formula we've got. So our equation is x minus e squared plus y squared equals d squared, which hopefully you recognize as a circle with center E, 0 and radius d. So let's start by drawing that up. So we've got, basically, with all these questions, as I've mentioned, I'm not giving certain values to D and E, so I'm just going to pick some point E that's going to represent the center of this circle, because we're at E, 0. Now, our radius D is some value that we know is less than E, so the circle isn't going to kind of breach into this quadrant, so I'll just kind of pick some arbitrary value for the radius that we'll call D. So here's my attempt at a circle, and we know that this radius here, the value is D. Alright, so what we're doing here is, as with the others, you kind of have to visualize taking this shape, in this case a circle, and having it rotated around the y-axis. So it kind of comes off the page and around and then back beneath the page and back, and you end up with a donut or a torus. So as I mentioned, we'll use the cylindrical shells method. So that's going to involve picking certain lines that become very, very thin, and repeating this process where for each line that we draw between our points, we rotate that line around the axis, and what you get is a cylindrical shell. And as I mentioned in the last video, if it helps, you can kind of picture it as if you're building something using paper mache. So getting really, really thin pieces of newspaper and just layering them up on each other until you end up with something with volume. So that's kind of what this technique is all about. And the key to it is, once you've kind of drawn up what you're rotating, is working out the dimensions of the cylinder that gets formed when you unwrap it. So this cylinder, if you unwrapped it, you'd end up with basically a rectangular prism. Because if you flatten out, if you kind of cut this cylinder and then flattened it out, you end up with a rectangle. And so what are the dimensions of that rectangular prism? Well, we know that the height of it is essentially dx, because that's the width of this line, the thing that we hope gets really, really thin. The length of the rectangle is essentially the radius of this circle, because we're unwrapping it. This circle has the circumference of the circle, not the radius. The radius is x, whatever x value we've drawn this line at, so that the circumference would be 2 pi x. And for this particular question, you need to be careful not to confuse your circles, because we've got this circle that we're rotating around, and then we've got this circle, which is the base of a cylinder, and you don't want to get those two circles confused. I could see a lot of students here maybe carelessly writing 2 pi d, thinking that d was the radius, but really it's x. And then the height, so the height here, well, from here to here is y, and we know that the circle is symmetrical, so this whole height would be 2y from top to bottom. And that's another potential source of error. Often we're only kind of looking at something bounded by the x-axis, and so often this is just y. And if you're just in the habit of not really thinking about what's going on, I could see a lot of students just writing y there instead of 2y. So definitely got to be careful here. But once we've got that basic layout, we can now write out our volume. So our volume will be equal to the integral between our two boundaries here. So these x boundaries would be e minus d. So that's what this value would be, e minus d. And this value would be e plus d. So there are our two boundaries of our integral. And the volume of this prism would be the area of the face times the height. Area of the face would be 2y times 2 pi x times dx. And now we just need to get this in everything in terms of x and then integrate it. So I'll just bring out my constants. So we'll have 4 pi times the integral of e minus d to e plus d of x times y. So we'll have x, and I want to get y in terms of x. So here we'd have y squared equals d squared minus x minus e squared. So y would be plus minus root d squared minus x minus e squared. Now in terms of thinking about the volume and what we're integrating, I can just put in the positive square root here, which really just represents this semicircle rotated. And even though I'm only putting the positive square root, I haven't missed out on this half because we've captured it by the fact we had 2y. So we're essentially taking this semicircle, doubling and rotating it, and then doubling it so that you capture the whole volume. So it's okay to just take the positive square root here. So we'll take square root of d squared minus x minus e squared, and then dx. So now we've reduced this to a integration problem. This is definitely a more complex thing to integrate than what we covered in the first two questions. So you can see some scaffolding here by the person who wrote these questions. They're kind of letting the difficulty build up. Now I think one way to tackle this integral is to kind of notice that if we can get the derivative of what's under this square root, if we can get that outside the square root, we can then use the reverse chain rule. So the derivative of what's under here would be minus 2x minus e to the 1, so minus 2x minus e. So let's think of how we can do that. So if I write 4 pi times the integral of e minus d to e plus d, I want an x minus e out here. So I'm just going to do e plus x minus e. So I haven't changed anything because I've added e and then subtracted e, times the square root of d squared minus x minus e squared dx. And now I think what I'll do is I'll just break this into two integrals. So we'll get 4 pi times, and it'll be e times this. So e is just a constant, so I can write it outside. E times the integral from e minus d to e plus d of the square root of d squared minus x minus e squared dx. So that's the first expansion. And then plus the integral from e minus d to e plus d of x minus e square root of d squared minus x minus e squared dx. So that's what we're dealing with. Now we're very close to having the derivative of what's on the inside out here, if I then just multiplied by -2, then we'd be looking good, but I can't just multiply by -2, so I'll multiply by -1/2, and then that way I haven't changed anything, but I could bring out that -1/2 and have this in the format ready for the reverse chain rule. So I'll just write that. So we'll have 4 pi times e times the integral of e minus d to e plus d of root d squared minus x minus e squared dx minus 1/2 times the integral from e minus d to e plus d of -2 x minus e square root of d squared minus x minus e squared dx. And now, whilst we've got two integrals that kind of look at first glance like they're pretty complicated, this one here, hopefully you see, is just asking for the area of a semicircle, i.e. this area here. And the area of a semicircle is very easy to evaluate. It's just half the area of a circle. And if you know the radius, the area is pi r squared. So that's going to be easy, and this we've set up so that we can use the reverse chain rule. So actually, whilst this integral looked like it could have been a bit of a nightmare, we've found a way through a simple little hack to get it into a manageable format. So I might just have to turn over just so that I get some space. So let's turn over and we'll have volume is equal to 4 pi times, and now if we, and there'll be an E, and then times the area of a semicircle. So the area of this circle would be pi d squared, so we're going to get pi d squared on 2. So that's that bit, easy. And now it'll be -1/2. And maybe I'll just rewrite this whole integral so I can do some side working on the reverse chain rule. So the integral from e minus d to e plus d of -2 x minus e times the square root of d squared minus x minus e squared dx. Now over here I'm just going to do the side working for the reverse chain rule. So if I let u equal what's under this square root, so d squared minus x minus e squared, then u dash, or in other words du dx, would be equal to -2 x minus e. So now I could see that what I've really got here is the integral of essentially du dx. So that means du would be this, and this would just become du, and then this is just u to the half. So we get u to the half du. And that's very easy to integrate. That would just become u to the 3 on 2 on 3 on 2, or in other words, 2u to the 3 on 2 on 3. And now all I do is insert u back in, and we've got our integral. So bringing this back up, we get equals 4 pi, bracket, e to the pi d squared on 2, -1/2 times, and this would be 2 on 3 times d squared minus x minus e squared, all to the power of 3 on 2, and we're evaluating that between e minus d and e plus d, and there is a bracket here. Alright, so let's evaluate this. So we get 4 pi times e pi d squared on 2 minus a half times, now if I put E plus D in here for x, that would be D squared minus E plus D minus E would be D squared. So we get D squared minus D squared is nothing. So we'll get nothing minus, and if I put E minus D in here, we'll get E minus D minus E, or minus D. So D squared minus D squared would be D squared minus D squared, also 0. So that all simplifies to 0. So this all disappears actually. And so we get 4 pi times pi, we'll get a pi squared there. E d squared on 2. The 4 and the 2 will simplify to just be 2 pi squared E d squared units cubed. Alright, and so that is, that's the volume. Now, here we actually have a check, a handy check that we could do to just make sure all of this integration actually worked and there weren't any errors. And the check here is, we know that the volume of a torus in general, I mean you might not know this, but if you did, the formula for the volume of a torus, in general you can write as 2r pi squared r squared, where in this format, capital R is what's called the major radius, and that's basically the distance from the origin to the center of the circle. So in our form, that's E. The major radius would be equal to E. And then little r is what's called the minor radius, and that is equal to the radius of the circle that you're dealing with, or in other words, D. So if we just substitute that in, we'd get 2e pi squared d squared, which with the minor rearrangement is 2 pi squared e d squared units cubed, which is what we worked out. So that gives us some comfort that we haven't made a mistake in our integration. So yeah, there you have it. That's how you tackle that question number 3. Definitely a little bit more difficult. Plenty of spots to get caught up. You've got to be careful not to make mistakes in terms of what's really happening as we rotate this circle. That's, I think, challenge number 1. And then challenge number 2, which is working out how can you tackle this integral, because the integral was definitely more difficult this time around. I happened to go down a path that let me use the reverse chain rule and noticing the area of a semicircle. I'm sure that's not the only way. There's probably other ways that you could evaluate this integral, but this is just what leapt out at me as being what was going to be a path of least resistance. So yes, hopefully you found that explanation helpful. If it was helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.